Hi there, welcome back to Petrophysics Rocks, my new YouTube channel. Things are starting to progress quite well with the channel now. Got a few subscriptions, got a few likes, and we've got some comments in the remarks sections down below. And that's all great interaction, and it really is appreciated. It helps drive the YouTube algorithm, and hopefully will help me get my my videos out to a wider geotechnical audience. Obviously, as I said before, I'm not really going to go mega viral with any of these things, but I'm sure there's a larger technical audience out there that would appreciate a quirky look, an alternative look at some of these issues. Now, we're kind of getting towards the end of the videos that I'm transferring from my old website onto YouTube. So unfortunately, I'm going to have to start doing some real work now and putting some new material together. So if you have any ideas or any subjects that you'd like to see me have a go at, and if I have some experience of them and I have the material, then I'll happily try and address them. So pop in the remarks down below, any questions that you have or subjects that you'd like me to see me tackle, and I'll certainly add them to the list. Now, I can't guarantee any particular time scale or timetable to get them done by, but hopefully if we add them to the list, then they will float to the top like cream, and we'll certainly get around to them as soon as I can, if you like. Now, this particular presentation brings us to Stonehaven. Stonehaven and Dunnottar Castle, which is just south of Stonehaven, which is just south of Aberdeen. And the reason that we're here is because this beautiful castle is actually on rocks and cliffs made out of rather spectacular rock called conglomerates. And these conglomerates are cobbles of rock in a matrix of sandstone, and you see that they're held in that. Oh, really? I do apologize. There'll be no cheap, tacky tricks like that anymore. We'll just carry on with the proper rocks now. As you see, they're rather spectacular rocks. They're these cobbles of rocks that are held in a sandstone matrix. And if you've ever walked across a river or near a beach where these rivers come out to the sea, you'll often see these large cobbles held and suspended in a sandstone matrix. Now, offshore, hopefully by now you'll understand the basics of storativity and where oil is stored. The oil is often stored, or can be stored, in the sandstone matrix around these boulders, these old boulders. Now, this particular rock here is quite old. It's Devonian, which, if you look up on a geological timescale, is quite early on in the Earth's history. Devonian old red sandstone, and you'll see that the ones offshore that we deal with are primarily out there in the North Sea, are a bit younger. They're of Jurassic age, although actually some of the cobbles, these boulders in the Jurassic reservoirs of the Bray area and the T-block area, which is the one that I've been working on, the actual cobbles themselves are oftentimes of old red sandstone age. So geology does that now and again. It kind of recycles stuff, reworks material. So the old Devonian rocks can be reworked later on into our Jurassic reservoirs. And the challenge that's presented by these conglomerates petrophysically is that you've got two types of sandstone, if you like. Now, predominantly is, if you recall, Petrophysics for Dummies, a good reservoir rock is sandstone. But there, you can imagine, these are two different types of sandstone, very close together. You've got old red sandstone cobbles and perhaps a younger sandstone matrix, the beach sand around it, if you like, the fluvial stuff that flows around and supports these cobbles, and they're all quite close together. So as you bring a logging tool past, the logging tool measures two types of sandstone. Great, and it gives you the average properties for those two types of sandstone. And the challenge that we have petrophysically is that Not all sandstones are created equal in this capacity, and therefore the oil tends to be in one type of sandstone, the matrix, and less so in the boulders. And you'll see that some of the boulders do contain a misting of oil and some potential of oil. Some of the younger boulders might still have some porosity and permeability to allow oil to get in. And to unravel all that and to work out what oil is what oil is where, can be quite tricky. So this particular presentation that I worked on is one of my favorite presentations, or one of my favorite pieces of work, actually. It's called Conglomerator, The Trouble with Rocks. And the Conglomerator is a random number generator that I put together in Excel. And it basically simulated what these rocks look like in Excel, such that when you take the logging average of them, you can get a good idea as to what properties of the matrix and what properties of the cobbles exist, and therefore back out how much oil eventually is in the matrix. Now, I've also used this kind of technology, if you like, in a thing which I called the drillulator. So I've got the conglomerator, and I've got the drillulator, and I haven't made a presentation on the drillulator yet, but basically the drillulator is a simulated oil reservoir in Excel that you can drill up and get well results from by drilling different parts of this Excel spreadsheet. Anyway, if I get around to making that presentation, I will explain it all then. But here with the conglomerator, we use this in conjunction with some image analysis techniques to basically work out the clast to matrix ratio from core photographs of this really spectacular rock. You can work out what is the correct ratio, proportion of cobbles to matrix, and therefore use the conglomerator to assign properties to those different fractions, and then do your best to work out what the ultimate distribution of hydrocarbons is. As you'll see, hopefully it's explained a little bit better in the presentation, but I hope you enjoy it. They are spectacular looking rocks, if not the most widespread reservoir rocks around the world. As I say, I'm sure conglomerates exist in other countries as well, but they're probably, I assume, not the major reservoirs that most people are interested in. But like most of the things that interest me, they're a little bit quirky and a bit unusual, and they provide a bit of light relief. So very enjoyable to work with. And perhaps it might plant a seed in your mind as to where you might be able to apply this technology in other fields. As I say, the drillulator is one example that I might get around to sharing with you at some point. But for now, hopefully you'll enjoy this presentation, the conglomerator, or the trouble with rocks. Okay, thank you very much. Hope to see you soon back on the channel before too long. Remember, click and subscribe would be much appreciated. Thanks a lot. Cheers.
Hello, I've called this presentation Conglomerator, or the Trouble with Rocks. Now, it's a bit of a niche presentation. Not everybody's going to encounter these types of issues, or indeed have to cope with these types of rocks. But nevertheless, I've enjoyed tackling it, and I thought I'd share with you some of the techniques I've used, and you may be able to find some application for them in the work that you do, even if they aren't involved directly with conglomerate reservoirs. Okay, so an outline of what I plan to go through. The problem, basically, I'd like to describe to you the problem that we have petrophysically, dealing with little rocks in big rocks, and the problems that they pose for petrophysical analysis. I'm going to show you some stuff about quantifying the core, using core information to give us a better handle on characterizing the nature of conglomerate reservoirs, and then how we use that information to set the expectation. What will the impact be on our conventional log analysis? I've created an Excel spreadsheet that I call the conglomerator, that runs a petrophysical simulation to give us an idea of the impact of some of these petrophysical properties that we observe from core. Then from that we'll work out how much are we missing in our conventional log analysis. When we take a conventional set of logs over these types of reservoirs, what are the sorts of things that we're missing, both in terms of hydrocarbon pore volume, and I'll even touch on some flow characteristics. Then after that, obviously, we have to get into applying some of this information in developing log analysis techniques to derive petrophysical analysis away from cored wells. In fact, I probably won't be touching too much on that. That's kind of work in progress. I may hint at a few things, but primarily I'm going to concentrate on the work that I've done with this thing that I'm calling the conglomerator. Okay, so for the first time I'm not going to do this presentation in PowerPoint. I'm going to go straight to this Excel tool that I've created called the conglomerator. And hopefully it'll fire up here. Here we have a photograph of some conglomerate rock outcrop. This is how it might look if you were to see it on a beach. These are ancient rocks. This is all quite well cemented up. Here we've got cobbles and pebbles, you can see, of large bits of rock, all in a nice sandy matrix. Here's a sort of another photograph that's a bit zoomed in, and you can see the nature of this rock. Now over here we have some core photographs from one of our North Sea fields. So we've encountered, we've drilled a well, and we've actually encountered this rock in the subsurface. And this photograph is taken under ultraviolet light, and you can see that the oil is glowing, a nice golden brown color, slightly bluish tinge to it. And you can see here a number of cobbles, some of them rounded, most of them quite jagged. Quite a mixture, quite a spectacular looking rock. Now actually, in reality, a lot of these pebbles here are not fluorescing with oil. That's a mineral fluorescence rather than an oil fluorescence. So a lot of these cobbles actually don't contain much oil at all. And so that's the concern that we have as petrophysicists, is that we've got some rocks here that are essentially little rocks of little blobs of sand within sand. So how can we tell those apart in the log analysis? It's quite tricky. It's all sand together. What does it look like in logs? So let's have a look at some CPI logs from this reservoir. And in fact, that spectacular rock, it doesn't look so spectacular in log analysis form. Here is a density neutron display, and if you recall the Petrophysics for Dummies presentation, you'll recall that over here in Europe we scale the density neutron with 3 or 4 pu of separation in it between the two logs, so that the geologist can colour it in yellow. And what you can see here is actually quite a monotonous large tank of sand. Really doesn't have much character to it at all. Doesn't look as spectacular as the core photographs at all. This one's got a little bit more going for it. It's got a little bit more variation in porosity. Porosity over here comes and goes, but generally the logs themselves look pretty monotonous. Here you can see we've had an attempt at identifying some of these conglomerate intervals, and even though these intervals we think contain quite a large number of these pebbles, you can still see that we have still a reasonable porosity, and we calculate quite a lot of hydrocarbons associated with them. So one of the concerns that I have is that this is a Jurassic reservoir, and a lot of the cobbles are much older sands, much older pebbles from of Devonian age, and they tend to be much lower porosity. So I was worried and concerned that maybe some of the resistivity that we encounter here, you can see the resistivity curve. Now that's normally associated with increasing resistivity is increasing oil saturation, but what if we had just increasing amount of low porosity, highly resistive pebbles of sand which didn't contain any oil but might contribute to the increase in resistivity? Are we, or were we, overcooking the hydrocarbon estimates in these conglomerate reservoirs? Because as you can see, it's difficult to see on the logs where the conglomerates are. And then looking at the core, you kind of think, well, is that all oil saturated, or some of those cobbles not have much oil in them at all? Well, we kicked off a project, and our friends over at Synergy came up with some software that allowed us to take the core images, the core photographs here. Here's some white light photographs here. What do you mean? Here you can see some white light, and here is the UV photograph equivalent, and here you can see what I'm talking about, that mineral fluorescence. Here's some sandstone rock, and here it slightly fluoresces due to the minerals within it. And then we take these images and we convert them to black and white images, and then we can work out the proportion of black to white cells, and therefore we can get an estimate of the classed matrix ratio. Okay, so we have to be a little bit careful with some of these holes here. These are where the core plugs were taken and our petrophysical measurements were made, and on these images they tend to look like little clasps, but we can make corrections for those, and we get an idea when we look through all of our core data the proportion of pebbles within our reservoir. So we've got that good information from the core. We've got quite a lot of core, so we have a fairly good handle on the class to matrix ratio, the proportion of clasts in our reservoir. Now, our geologist as well, Mark Jones, he's done a very good job of going through here and looking at all of the petrophysical results from these plugs and classifying them, and basically using that information we can extract the petrophysical properties of each of these fractions of the rock, both the matrix and the clasts themselves. So knowing the clast properties, the matrix properties, and the proportions of properties, we can go on to have a bash at understanding the bulk reservoir properties. Now we have to implement this information and use it away from cored wells, because not all of our wells are cored, so we have to come up with a technique that takes the logs and is calibrated to this information and come up with a petrophysical model. Now to do that, there are several assumptions that we have to make when we don't have this core data available to us. So what I thought I'd do is take the core information, this core observations, and calculate some properties, if you like, and simulate them in Excel to really try and estimate the magnitude of the effects that I would see in my log analysis. So basically, using the core information, I was interested in knowing what sort of effects would we expect to see on the bulk properties of our rocks, and therefore give me a target to aim for when we're calibrating our log analysis techniques. So here I have created a synthetic cell, if you like, a grid of 10 by 10, 100 cells, which we can consider as a random distribution of porosity. And I've used the Excel function random number generator here. Here if you see, I basically say in this particular cell select a random porosity from a porosity distribution. Now I've defined the porosity distribution for this particular example to be with an average of 12 pu and a standard deviation of plus or minus 0.03. And Excel goes away and looks in my normal distribution sheet, where I have a bunch of normal distributions of various properties, and it goes in there and it looks up properties for my random number from that normal distribution. And you can see that in this particular cell it's selected a random porosity of 6. So it thinks this cell is 6 pu. Now because it falls below my net cutoff of 10 pu, it's assigned it 0 net to gross. So it said it's non-net, it shaded it in brown, and it's assigned it non-net in my net to gross grid. Similarly, this cell here has selected 15 for some reason, and that satisfies the net criteria, so it is net, and it shades it in yellow, and yellow here on the net to gross grid as well. So what I can do then is I also can take a saturation for that porosity. So I can say, okay, if I'm a net piece of rock, net cell, take that porosity and look up a water saturation in my water saturation grid, my water saturation population, and my net water saturation, I'm saying on average, is around about 20% water saturation with a standard deviation of plus or minus 0.06, and in this case you can see it selected 12% water saturation. Now this cell the first cell in the block is a non-net one, as we said before, and it's going to select a water saturation from the non-net water saturation distribution. And in this case I've said that non-net rock generally has a saturation of around about 80% plus or minus 0.10. You can of course make this a bit more consistent with the porosity by using a bulk volume of water term, so that your porosity and your saturation are a little bit more linked. But in this particular example I'm just choosing random saturation. So I populate my saturation grid, which corresponds to these 100 cells, with saturations from the appropriate distributions. And you can see that for this grid of 100 cells, my average porosity is 11 pu, and the average water saturation is in fact 33 pu, which is a combination of the average saturations from both the net and the non-net cells. You can see here that I can confirm that the net saturation from the green cells is just 19 saturation units in this sense, which is pretty close to my target input saturation. And the nice thing about Excel is obviously that you can run the simulation a number of times, pressing F9, and you get a random selection of porosities, and each time it selects whether they're net or non-net and selects the appropriate saturation. And you can see that I calculate an average saturation for each distribution. So as I click this, you can see that my gross porosity is around about 12 pu, which is the target porosity I wanted for my particular example of reservoir rock. 11%, 12% porosity, and on average it has a water saturation of about 30% overall. Now if we calculate up the volumes for that, so we have 88 cubic meters of rock. If each of these were a cubic meter, doesn't really matter what the units are, but we have 88 cubic meters of rock, which leaves us around about 12 pu of porosity left, 12% holes, of which 8 to 7 to 11%, 11 meters are oil, and the water volume is around about 3 or 4 cubic meters of water. So we can calculate for this particular simulation the appropriate bulk volume of oil in our pore system. Okay, so that's a very simple conventional bulk analysis. If I go on to what I call the conglomerator, here I've added an extra term here. I've put in a grid here that represents the clast to matrix ratio, if you like. So I've said, let me call myself a clast if I trigger 1, and I'm a matrix if I trigger 0. So the clasts are all 1s here, and you can see that the average class matrix ratio, as I click this, is around about 50% most of the time. And so 50% of these cells are class, and then I use that. I say, right, well, if you're a clast, look up a porosity from my class porosity distribution, which is one of these distributions over on this sheet here, class properties over there on that sheet. If you're a clast in this cell, then look up this class porosity from that distribution. If you're a piece of matrix, then look up this matrix porosity from this distribution. And then similarly, depending on the net cutoffs, I've decided let's just set a net cutoff of 12 pu in a clast. It has to be over 12 pu before it's net reservoir. And in the matrix I've said, okay, anything over 7 pu, that could be matrix, that could be reasonable reservoir quality. And then depending on whether this is a clast and whether it meets the cutoff criteria, I assign a net to gross parameter based on both whether it's classed or matrix and whether it satisfies the criteria. And in a similar way, I look at the water saturation depending on whether I'm a clast, and if I'm a clast, I look up my water saturation, and let's say that on average the majority of the class, in fact, we found are pretty non-oil bearing, so they have a pretty high water saturation on average, about 90%, let's say. And if I'm a piece of matrix, then I'm allowed to have a water saturation that's as low as 20. And I can simulate that, and I can run that a number of times, and then I can similarly calculate the gross hydrocarbon saturation, or gross water saturation. 1 minus water saturation is the hydrocarbon saturation. So here you can see I've got a gross porosity again of around about 13 pu, and a gross water saturation for this particular block of rock of about 31 pu. So pretty similar to my conventional log analysis. And you see, if you take the percentage difference between this conglomerator and the of conventional analysis, you can see that I'm pretty much around the same place. Now, that was my fear, that was my worry, that I had 4 pu old red sandstone cobbles in a nice 20 pu highly permeable Jurassic matrix, and I was worried that that was going to impact my hydrocarbon calculations, my hydrocarbon volume calculations. Now, if you look at the literature out there for these types of reservoirs, you often find, in fact, that the class porosity is actually a bit higher than 4 pu on average. Now, we obviously know the class porosity of our reservoir, but I'm just going to put in this industry number, if you like, this published number of about 10 pu. I'm not going to confirm or deny whether our class are the same porosity, but if they were about 10 pu, let's just take the average from the literature. Now you can see that my porosity's crept up to 15% gross on average. So just to keep that down to 12 pu, let me just put this, my matrix porosity, let me assume that my matrix porosity is only 15%, and I'm back down to my gross porosity of 12 pu. So in fact the porosity is the same in this case, around about 12 pu, but this time you see that my water saturation has gone up quite considerably. So I'm up to 40 or 50% water saturation for the whole 100 meter cubic block. Now, I've still got low net water saturation, so don't be alarmed. This is the things that's going to be flowing, typical 19, 20 pu, 20 saturation units in our net reservoir. But overall, the bulk volume of rock, bulk volume of oil that I'm interested in has actually dropped by about 25%. So that's interesting, and so that's could be perhaps if this class matrix ratio is appropriate, that could be the expected porosity reduction, the hydrocarbon pore volume reduction we could expect if these classed and matrix properties were true in our reservoirs, or indeed your reservoirs. So let me just flick that a few more times. Yep. Okay, so you can see here that it's about 25% reduction compared to the conventional log analysis for this same porosity. Now, we have a range of gross porosities in our reservoir, so that's not exactly a global number, but nevertheless you can see it's that sort of order of magnitude. Now let me just show you some other thing here. Let me just come down here. If I take this information and if I have a look at it on a if I take those 100-foot blocks and instead of having them in a nice square matrix, if I laid them out, if I drilled through those blocks, this is the porosity distribution that I see. And here's a histogram, in fact, so maybe it might be a bit clearer. You can validate here. I've got in this particular realization, I've got 58 class and 42 matrix points, and this is the porosity distribution that I have. Remember that I said my matrix is around about 15 pu on average now, and my class are around about 10 pu on average. And this is this particular realization. This is the porosity distribution. If I look at the classed porosity in this particular case, on average it's, in this particular one, it's 9.76 pu. The matrix is 14.88 pu on average, and all of those samples together, all 100 of them together, give me this 11.91, or about 12 pu on average on the bulk properties. And here's a little photograph of the rocks just to remind you what they look like. And as we flick through the simulations, you can see that we've got this sort of overlapping porosity distribution, and you can see that this is what a log would look like if you drilled through 100 of those meter blocks. Now here I've also put in here the red curve as a sort of an illustration for what a wireline log might be expected to see, given the porosity distribution and the resolution of that change. Here's a typical sort of a wireline log response over that, and you can see that we obviously lose the extremas. We don't manage to pick out the high the high porosity streaks, and similarly we don't see the low porosity streaks, and that's typical. Remember what our CPIs looked like, rather monotonous and not as spectacular as the core. Perhaps this is one of the reasons for that. So if I just change this back to this magnification, one of the issues is, what is the clast matrix ratio? Okay, so if we have no class at all, what do we see? We actually get, if we replace all of the class, if everything is 20 pu rock, then in fact, obviously, if everything was 20 pu rock, well, obviously, it'll be a higher oil volume than our average 12 pu rock. So if we go down here and we run the simulations for different classed fractions, okay, you can see that as we increase the fractions of class through here, you know, we reduce the amount of hydrocarbons, as you might expect, calculated remaining in the bulk volume of the rest of the rock. So here we go, as we increase the percentage of class, some of them still may classify as net and still have some oil volume in them, but nevertheless we see a general reduction of oil volume with increasing class matrix ratio. So as I run this simulation here, you can see that as class percentage increase, our class matrix ratio increases, the reduction in hydrocarbon volume gets more significant. So if you have these types of reservoirs, maybe you have an idea of where you are on your class matrix ratio. Maybe you can pick a point along here to work out how much reduced your saturation, your hydrocarbon pore volume will be affected by. Okay, so this is all based on a simulation of the core data, the core information. These are the magnitudes of the expected reductions that we might see in our hydrocarbon calculation. Whilst I'm here, let me just flip over to this pseudo log creator tablet here. When we have to implement this in log analysis form, it's not really that convenient to have a single value for the classed porosity. Obviously, if you have to implement a class porosity in your log analysis where you don't have core data, if you assign all the class 10% porosity and you happen to have an 11% porosity cutoff, then you're rapidly going to switch off all the class altogether, or you're going to have them all on. So it's going to be a very binary on-off switch for the class, and that's not really what we see in our in the literature or in our core data. We have a distribution of class porosities, and what I've done here is I've basically created a sort of a pseudo log of class porosity that we can import into our log analysis. And as we change this, you know, we have a random number generator that sort of simulates a range of class porosities that we can put into our log analysis software where we don't have core data, and then the rules that we apply are appropriate. They're calibrated to the core data, but we take into account the fact that some class are indeed net and may have hydrocarbon in them if they have a reasonable porosity. Some of the Jurassic intraclass are not as severely handicapped, if you like, as the old Devonian ones. So this tab actually just calculates a set of logs, pseudo logs that we can cut and paste into our log analysis software. Okay, so actually one more thing I was just going to touch on before I leave is this under construction nomenclature here. Let me see if I can put this now. What this is here? Let me just take the wraps off this. Is that appropriate? Yes. Let me just take the wraps off this. Is an estimate of permeability. So, having got a handle on the bulk volume of hydrocarbon reduction, one of the things I'm interested in is permeability and how that might flow, and particularly if we're calculating some wireline logs here and we're missing these high porosity pieces of rock, it seems reasonable that we'll probably miss the high permeability streaks as well. Now, from our machinations, we can estimate a different poroperm trend. Here is a cross plot of porosity and increasing permeability here, and we might say that for the classed population we have one particular poroperm relationship, and the matrix population may have a higher permeability and a different poroperm relationship. So here is the classed here's the classed poroperm relationship, and here is the matrix poroperm relationship, and we can run a number of simulations on that, and we can calculate a permeability for each of these points through the log, and we can cumulate that up here. So here we are as a cumulative KH, and we've got say this is 49,287 millidarcy meters, I guess. If we assume that those were meters, doesn't really matter what the units are, but that's we've got 49,000 of them, whatever they are. So that's the permeability, the cumulative permeability thickness using this trend. So if you're a classed porosity, you'll use this poroperm trend, and if you're a matrix porosity, you'll use that poroperm trend. And if we add up all of those along the wellbore, we can get the permeability thickness. So we can do that, and we can see that permeability thickness ranges from 42 to 78, so quite a large range. These are very large numbers that we're dealing with. You may notice here I've just clipped this at 5,000 millidarcy feet. Okay, so those are the trends that we employ. It's perhaps a little bit more realistic if we put some noise in. There you go, that looks much more like core data now, doesn't it? There you go, so those are still using those same trends, but I've put a bit of appropriate, shall we say, noise into each one of those trends, and you can see that that's the resultant permeability curve. Now, one of the things that we do every day in our day-to-day life, if this was a set of core data, you might imagine that we might fit a line to that core data, and I'm just going to fit a very simple Y on X line. If you know my permeability, flow condition permeability presentation, you know I don't like the Y on X line generally, but here might be a line that you might fit through both of those sets of data. Here it is, it's a Y on X log linear regression, so therefore it's a by essence it's a geometric fit. You can see my permeability presentations for why I don't like that necessarily, but you can see here that if that was happened to be a real set of core data, that's a regression line that some petrophysicists might come up with. Now, if we applied this porosity line, this poroperm relationship line from our pseudo core data to our log porosity curve here, this is this curve here, if we applied that poroperm relationship to this porosity curve, we would get this KH curve here. So here you can see I'm calculating 2,000 millidarcy meters of KH. So that's quite a dramatic difference. There's quite a lot of permeability we're missing out on. Here I've got 4,000. And if I run through some simulations, you can see that there's a couple of things going on. In fact, there's probably three things at least going on here. Clearly, with a single poroperm relationship, ignoring the facies information that we have from core, you're missing out. You're applying one poroperm relationship to two facies. Not so good. Clearly, you can see because of bed resolution issues the log porosity we've got is missing the dynamic range, so we've got a reduced dynamic range in porosity, so of course we're never going to capture the highest permeabilities seen up here. There is this y on x log linear thing that is a geometric fit, so really if we were doing my preferred fitting techniques, we would probably be closer to this yellow line for all of the curves actually, because we'd be fitting through the arithmetic bin averages, so in fact we'd be ignoring a lot of this lower trend, so we'd probably be overestimating it, I guess, in that sense. And here I've put down here some numbers. Here's by the way, there's a little cartoon down here. This was some interesting work done on a face of some of this conglomerate slab, where mini-perm probe data was run on the face of this core of some of those conglomerate photographs that you saw, and you can contour up the permeability map, and you can see that these clasts here form these low permeability pebbles, and yet there's quite high permeability through the matrix here. It's quite a nice little contour map of permeability just to confirm that actually they behave in very different ways, the matrix and the class. So here are some statistics. Here's the average arithmetic. Let's just deal in arithmetic average terms for an example. Yeah. So in this particular realization, the class permeability is 4 millidarcies. The matrix permeability is 743 millidarcies, and the bulk permeability from the from everything together, just actually taking the absolute average of the 100 grid cells, is 314 millidarcies. Now the estimate that we would get of that permeability from the wireline log and the wireline log poroperm relationship is only 10 millidarcies. So let's run this through a few times. You can see that I'm getting 10 to 40 millidarcies from my wireline log, and yet the known absolute answer of arithmetic permeability should be closer to 700. So that's quite a dramatic difference. Now clearly, whether you should be using an arithmetic average, I kind of think so for the matrix. You can assume probably that all the matrix is connected, so therefore an arithmetic averaging technique might be more appropriate. And perhaps, I guess, with the clasts, they occur randomly and sporadically, and perhaps you can bypass them, so perhaps a more geometric average, they act as more like baffles, might be more, a geometric averaging approach might be more appropriate for the class population. But I think what I'm trying to get at here is that clearly the matrix performance is what really drives fluid movement in these conglomerate reservoirs, and by biasing our log analysis down to the bulk properties of the rock, we're never capturing the actual permeability that we see and is potentially held within the matrix. Okay, I hope that's reasonably understandable. I hope I haven't missed anything out there, but this bit is still a little bit work in progress, but the effects on permeability are quite dramatic. Okay, so let's just tidy that up now, finish that off, don't save any changes, and go back here to our PowerPoint presentation. So in conclusion, we've used the XL random function to look up properties from the XL probability distribution functions, in this case the normal distribution. Hopefully that might have given you some ideas of the sort of applications that you might be able to find it useful. This approach has allowed us to assess the hydrocarbon pore volume independently of cutoff criteria. So we're calculating the total bulk oil volume within all of our rock. Clearly you can get into confusion if you are talking about net volumes and gross volumes, and if your net cutoff suddenly switches off all of the conglomerate facies, then you've got a bit of a problem. But by using this type of approach, we don't worry about cutoff selection. That's another argument to be had down the road. We can calculate the oil volumes directly in a known bulk volume of rock. And I did touch on the fact that we used a simulated class porosity distribution. I guess distribution is the key word there, rather than assigning a single average value to our class porosity property. And this allows us to give us a much better match to our simulated results, carrying a range, a distribution in our class porosity. So when we correct for class porosity, it's not an all on or off switch. And then finally, I touched on permeability assessment, and obviously permeability based on the bulk average log properties, porosity, may be prone to significant error. Obviously, we've lost the dynamic range in our log measurement. We obviously have the problems of Fashey's differentiation. We may not realize that we should be using a higher poroperm trend for our matrix Fashey's. It might be difficult to identify that. Clearly, the network continuity may be problematic. Is all the matrix connected? Is the class matrix supported or class supported? So there's still some arguments or discussions to be had about whether geometric or arithmetic processes are better, but clearly there's a significant difference between the simulated grid and the likely log response. I hope that's been interesting for you and has provided you with some food for thought and perhaps some ideas. If you'd like a copy of the Conglomerator, I think a £25 donation to my Archie Children's Hospital charity page would be appropriate, and I'll happily send you a copy, and you can have a play with it and maybe adapt it for your own use. Okay, thank you very much for your attention.